Okay, so I want to get into the chemistry of anhydrides next. Now, the first thing I want to do is we'll get to the name anhydrides and why they're called anhydrides by looking at the synthesis of anhydrides from carboxylic acids. So let me just pull up my notes here, sorry. Where my notes go? Okay, they're there. All right, so what we can do is if we want to look at the synthesis, and this is going to be of symmetric anhydrides. What we want to do is take a carboxylic acid and we are going to expose it to Fischer esterification conditions. So that was some alcohol was added plus some H plus catalyst. And then we usually heat the reaction if you have gone through the Fischer esterification lab, and then we get out an ester, right? So we're going to expose ourselves to the Fischer esterification, not ourselves, the carboxylic acid to the Fischer esterification conditions, but I want to leave out the alcohol. And if I leave that out, I don't get the ester. Instead, what I get is the carboxylic acid anhydride. Okay, where both of the R groups are the same in this case. So doing a Fischer esterification reaction without the alcohol results in formation of an anhydride. Huh, that's pretty cool. So we leave out the alcohol, we leave something out, and we get a new compound, and that is the carboxylic acid anhydride. Now, the reason why it's the anhydride is because you take the carboxylic acid, you react with itself, you release water, and you form this new functional group after the water is lost, after you've anhydrous, I guess, the carboxylic acid called the carboxylic acid anhydride. So water is lost. Water is lost, hence the name, the anhydride. Anhydride, which sounds like anhydrous or dry. Okay, anyway, that's enough about the name. Let's get into the mechanism for this reaction. The mechanism looks a lot like a Fischer esterification. So the mechanism for anhydride synthesis looks like this. We first take our carboxylic acid, which is both reactants. We're going to use two of these carboxylic acids to form the product eventually. We're going to get things started just like we did with the Fischer esterification, where the carbonyl oxygen is going to pick off the acidic hydrogen. The acidic hydrogen reacts first, right? That's going to give you this species, which you could draw with carbon-oxygen double bond somewhere, or you could put the positive charge in the carbon atom, depending on how you drew your arrows in the first step. This is my style. But now we're highly electrophilic at the carbonyl carbon position, so we could have a carboxylic acid react. What I like to do is, again, let the non-hydrogenated oxygen of the carboxylic acid add, and that's going to push the electrons up. And we're going to get to something that looks like this. Okay. So we have the carbonyl oxygen from a second carboxylic acid that's going to add to that carbonyl carbon now that the carboxylic acid has been protonated. Okay, what that means for us now is we can lose this hydrogen and we can roll some pi bonds around to get to a neutral structure. Just lost a carbon there. That's going to give us this. So we've established the formation of half of our byproduct, which is the H plus, and we still need another OH to get to water, and we formed one of the carbonyls in our symmetric anhydride. Okay, so what's going to happen next is either one of these OHs is going to pick up the hydrogen atom to give an H2O leaving group, which can then pop off in a few ways. I'm just going to lose the hydrogen between the oxygen and hydrogen and then push off the water as a good leaving group. That's going to give rise to our final product, plus H plus H2O. So the H plus is our catalyst. The water is now gone, so we're anhydrous. I don't know what I'm writing. Okay, but we more importantly formed our anhydride as a result of doing the Fischer esterification reaction in the absence of an alcohol. Okay, so we made a symmetric anhydride. How do we make an unsymmetric anhydride? I know many people are like, unsymmetric, what do you mean? Do you mean asymmetric? Well, asymmetric actually refers to something with a stereocenter, which doesn't apply here. That's the other thing that students really like about finishing the semester with carboxylic acid derivatives is there's not much to worry about in terms of stereochemistry. Okay, anyway, let's worry about now what are called mixed anhydrides. So mixed anhydrides, these are carboxylic acid anhydrides without symmetry. Okay, so what I mean by that is if we have our anhydride framework, we put an R group over here, but that's different from the R group on the opposite side. So the R and the R primes are now different from one another. Okay, so how do we make this type of molecule? Can we do it under the Fischer esterification conditions without the alcohol, like we talked about before? Well, I suppose we would have to add two alcohols, though. Or excuse me, two carboxylic acids. You have to add two carboxylic acids. Seems a little problematic because we would get what's called a statistical ratio based on the relative rate constants for each of them, where we would have some symmetric anhydrides where you've got the R groups being the same and then some where the R groups are different. And it's not necessarily going to be a 1-to-1-to-1 ratio depending on the rates of reaction for each of these things, how basic they are, how nucleophilic they are, and that sort of thing. So there's a more predictable way. What we can do is we can just react carboxylates with acid halides. React carboxylates with acid halides. So what you could do is take some sort of acid chloride and react it with the carboxylate of a carboxylic acid. So you could generate that in a number of ways. You could even take the carboxylic acid and add base. We've actually looked at this reaction before, but just mixing these things together, we'll do an additional elimination reaction where we add the carboxylate oxygen, push up to make a carbon-oxygen single bond, now negative at the oxygen. Okay, so here's the oxygen that's added, carrying with it the R prime. So this is our addition step. This is our tetrahedral intermediate. And then that negative charge can come down to kick off the chlorine atom, which is the better leaving group. And we get to the second most electrophilic carboxylic acid derivative. That's the anhydride. So we start from the most reactive and we progress towards the least reactive. Okay? So, I guess we have a carboxylate here, which is the least reactive with a nucleophile, but that's because it's the most nucleophilic of the carboxylic acid derivatives, followed next by the amide. Okay, so here we have the carboxylate reacting with an acid chloride. That gives us our mixed anhydride in a very controlled manner. Okay, we're not going to have to worry about too much scrambling here. We could deprotonate the carboxylic acid if we wanted. And that would just mean taking our carboxylic acid component and reacting it with base within the reaction mixture. So we're actually picking up a carboxylic acid on the shelf, adding some sort of base to it, and we would see this rapid reaction where the base engages the carboxylic acid to form the ammonium carboxylate quickly. Make that base negative. Go ahead and push arrows. And there we've got our base now. Having deprotonated the carboxylic acid, the carboxylate is available to do its reaction. Okay, so that's synthesis of both symmetric and non-symmetric, or mixed, I prefer that term, mixed anhydrides under two types of conditions with mechanisms for each. Now let's talk about some chemical reactions for anhydrides. So not surprisingly, hopefully at this point, reactions of anhydrides include addition, substitution, okay, by addition, elimination with a nucleophile. So we're going to make actually less reactive carboxylic acid derivatives. So it's addition, elimination, and we have some nucleophile adding. Okay, so what does that look like? Well, in general, if we take our anhydride, and I'll get to mixed anhydrides towards the end here, but I want to talk for the first part about symmetric anhydrides, where the R groups are the same on either side. What I want us to recognize about these species is that the leaving group is actually, I'm going to make that a little bit smaller, excuse me. This whole thing is actually the leaving group. So it behaves like Cl minus. Okay, and that's because the negative charge that results after that leaves is stabilized by resonance. It's just a carboxylate ion. We talked about the stability of those when we looked at how acidic carboxylic acids were. Okay, so what we're doing in this case is we are adding some nucleophile, and we do addition, elimination to form a new carboxylic acid derivative plus the oldest carboxylic acid derivative, the carboxylate. I don't know if it's the oldest, but it's pretty close to the oldest. Okay, so how do we do this reaction? Well, what are some specific examples of this reaction, I should say? Well, let's go ahead and look at an anhydride, and let's do a reaction on it. So we're going to make, in this case, an ester, just like we did with the acid chloride before. So once again, we do need a base here. You typically want to use something a little bit stronger. You can get away with pyridine sometimes, but I like to, yeah, maybe you want to get away with, alcohols are always kind of troublesome because their pKa's don't quite match up. But let's just use a strong base. I bet we can get away with it. So if we use a strong base, we can deprotonate the alcohol and allow the alkoxide to be our nucleophile. And we can even do some step addition where we deprotonate the alcohol first. So add the base first to make an alkoxide. So what that looks like is this. Now, in some cases, you can use pyridine, but you can't all the time. So I'm just trying to be careful here, whereas it's super reliable with acid chlorides. Okay, now we're going to take that alkoxide and do addition, elimination with the alkoxide. I drew my benzene ring a little bit too close to my subtitle here. So let me drag that down. Okay. Now we get the anhydride involved. I'm just going to have phenyl drawn small over here. Okay. The negative charge is going to engage either one of these carbonyl carbons to push electrons up and onto the oxygen. Now I'm going to abbreviate both benzene rings as phenyl with a pH. Now between the two leaving groups, the negative charge is going to come down and pick on the other half of the anhydride to be the leaving group, as it's a more stable negative charge. Okay, that's going to give us our final product plus our carboxylate, which sort of stays put because we've got a strong base present. Okay. You can also react these things with amines, and that goes a little bit more easily, especially for primary and secondary amines. So here you can react these things with amines to make amides. Now the way this works, I'm going to start abbreviating it with pH for phenyl. I'm going to keep it that way. But let's go ahead and just switch to acetic anhydride. Okay. So we have acetic anhydride, and we can actually do this reaction in water because the amine is going to react so much more quickly than water. And we've done this. We used acetic anhydride several times during the course of Organic 1 and 2. But one of the first times was when we used it with acid anilide to make, when we used it with aniline to make acid anilide. Okay. So we can have some sort of, let's pick on an NH2 group. Here the lone pair is going to engage the carbonyl oxygen, push the negative charge up. That's our addition step. It's hard to know the order of events for sure. At this point, I'm guessing it probably makes more sense for a base to come in, and a base could just be more of the amine starting material. But now we've got an overall negatively charged species, which is going to then eliminate. So I'd call this the tetrahedral intermediate. Sorry, I did not finish my thought. But I could also call this the tetrahedral intermediate, just some intermediate along the way where this center is sp3 hybridized. But anyway, sorry. Negative charge comes down, remake the carbonyl, and then push off the stable negative charge leaving group, which is the anhydride. Okay, and we form amides. All right. So we're progressively working our way back. If we really wanted to, we could treat this thing with sodium hydroxide and make carboxylic acids and carboxylates. I guess I might as well show that. Okay, let's, if we've got amides, we've got esters, let's go ahead and talk about carboxylic acids and carboxylates. So if we take this and we react it with hydroxide in some form, we're going to form the carboxylic acid, which will probably be readily deprotonated if we're under strongly basic conditions, but I'll go ahead and just draw both forms. So the negative charge here adds, and then we eliminate. So there's our tetrahedral intermediate. We've added, negative comes down, pushes off the oxygen that will better stabilize that negative charge. We get our carboxylic acid and our carboxylate. So now we've hit on everything sort of to the left of the anhydride in terms of its reactivity with nucleophiles. That is, we're probably not going to make acid chlorides. That's increasing in reactivity. But we can go backwards and go to the lesser reactive things like the carboxylic acids, the carboxylates, the amides, that sort of thing. Okay, so we then eliminate, trying to highlight addition elimination whenever I can. Okay. So what I want to finish this up with is looking at reactions of mixed anhydrides. What you generally see with mixed anhydrides is that if you've got a nucleophile that has the choice between two of the carbonyls, there's going to be a subtle preference for one over the other, okay? So what I mean by that is you're going to get, we have like methylamine being added. What we could do is we could have the methylamine adding to this position or the methylamine adding to this position. And then we're going to do addition elimination. And we're going to get, I guess I'm going to take my arrow this way. And if we add to the left, at the end of it all, we're going to have this species plus the carboxylate or the carboxylic acid, depending on the base that we use or don't use. Or we could have the nitrogen adding to the opposite side to give us this species, plus this carboxylic acid or carboxylate. Okay, so the point here is 4 products form from nucleophile addition to either carbonyl. Okay, so nucleophile addition to either carbonyl results in multiple products. Okay, so we have multiple products being formed. Generally, all products will be observed. Now, we could, if we had more time to like go into the lab, we could go and figure out like a major and minor preference for some of these, but it's very like situational dependent. I can't give you anything that will allow you to really predict for sure which one is more likely to be the major product in all circumstances. So, you know, if we could, like in the middle of a test, okay, imagine a test where I'm like, okay, I want you to go into lab and set up this reaction. It'll take you a few hours, and then run an NMR, interpret the NMR, compare it to some standards without your notes, and then we'll figure out which is the major and minor. Okay, let's you know, so then you can like do the lab. Anyway, my point is, if you want to know what's the major and minor of these, which pathways preferred, for the most part, you're probably going to have to go into the lab to figure that out. So don't worry about major and minor. This is a situation where what I want you to know is that if you have a mixed anhydride, multiple products will be formed because either of the carbonyls can accept the nucleophile. So that's the purpose of me talking about this. So I want you to recognize that opportunity for the nucleophile and predict all of the products as opposed to just the usual major derivative along with the carboxylate byproduct. So don't worry about major and minor products, just show all 4. Okay, otherwise that'll do it for anhydrides. Again, we're stepping back in reactivity from the most reactive, the acid chloride or acid halide, back to the anhydride. Next, we'll look at the ester. We've already kind of talked about the carboxylic acid and the carboxylate, so then all that remains after that is the amide. But that then leads us into the interesting chemistry of amines. So nice segue towards the end. Okay, all right, with that, we'll see you next time.